Hello, my name is Professor Rad, and today we are going to do a little bit of experimentation with decimals, particularly multiplying decimals together. So far we've discussed addition and subtraction of both whole numbers and decimals, but we only explored multiplication and division of whole numbers. So we've kind of held off on decimals for a little bit, and that's because they're a little bit more complicated. So what mathematicians do when they try to expand a process that they already have for something they know is they start to experiment with the unknown and look for patterns, see if there's anything familiar or different going on, and see what they can do with that. So that's what we're going to do here, and we're going to use this calculator here to assist us in this process. So the first thing that I'm going to do is I'm going to take this number. Oh gosh, I wrote it the wrong way the last time. That would just be like me, wouldn't it? But we're gonna take this number 543.2 and notice that we're multiplying it by basically like one more decimal place out. So we start out with multiplying by 1 and then 0.1, 0.01, 0.001, 0001, quadruple 01, right? So our goal here is to see if we can find a pattern if all we're doing is changing the number of zeros between the decimal point and the 1. So even though 543.2 is a decimal, I'm going to suspect that when I multiply by 1, nothing changes, because from our whole numbers, anything times 1 was itself. So let's see if that is true on the calculator. 543.2 times 1. Oh, this is the weird calculator. So it's going to give us 543.2. So my little guess there is correct. Nothing changed when we multiplied by just 1. But now what happens if we multiply by 0.1 instead? Now we get 54.32. Okay, now let's see what happens if we multiplied by 0.01. We get 5.432. Do you sense a pattern developing? Let's see if you can predict what the next one's going to be before we find it. So we've got 0.5432. Tack another 0 in there. And now there's a 0.05432. So I bet the next one, there's going to be another 0 in there in between. Ooh, so now what my calculator is doing is it's throwing the answer in scientific notation. Great job here. So we have 5.432 times 10 to the minus 3. So as a review, remember this minus 3 means we're going to move the decimal point to the left 3 places. 1, 2, 3. So we do indeed get 0.005432. Now let's try, instead of, we're going to come back to this in a moment, but let's try, instead of multiplying by shifting that decimal point, like that 1 being shifted over after a decimal point, what happens if we tack zeros onto the end? So we know if we're multiplying by a whole number, like if I had 6 times 100, I could just do 6 times 1 and tack on 2 zeros. But is that going to be the same thing if my number I'm multiplying by is a decimal instead of a whole number? So let's try. So I have 6.789 times 1, and I suspect this is going to be the same. Yeah, 6.789. Now what happens when we multiply by 10? 67.89. Okay, let's multiply by 100. 678.9. Do you notice what's happening? So let's see, I bet this one is going to be 6,789. So let's try. Yeah, 6,789. And we'll multiply by 10,000. 67,890. $678,900. So one thing I noticed right away is it's not exactly the same thing as what happened if I had a whole number, right? If I had 6 times 100, that would be a 6 with 2 zeros. And when I multiplied the decimal by 100, I didn't quite get there. Like I didn't get 6.789 with 2 extra zeros. But there is something that happened that is based off those number of zeros. So the two questions that you might ask after you do something like this when you're trying to establish a pattern is what seems to happen every time we move the 1 over a place. So either moving it over 1 place to the right or moving it over 1 place to the left. What happens? So those thoughts that we're having here when we're trying to figure out what happens, that's what mathematicians do when they're not sure about what something is. They look for patterns, and then based off of those patterns, they might form a hypothesis or a conjecture. So a hypothesis or a conjecture is an idea that you suspect is probably going to be true based on patterns that you've observed, but it hasn't been mathematically proven. So math is this sort of interplay between inductive reasoning, which is what we're doing here, observing patterns and trying to make a guess as to what's going to keep happening, and deductive reasoning. And deductive reasoning is when you're writing a proof, when you're saying, or you're applying like a general rule to specific cases. So here we might form a hypothesis that however many places after the decimal point the 1 is somehow connected to the movement of the decimal point when we multiply. Or how many zeros are after a 1 in a whole number, if we multiply by that, that's going to impact how many places that decimal point actually goes over. And a little bit of a spoiler here, we've actually been doing this with our scientific notation. And when we talked about percent, when we use those shortcuts of moving decimal points, we're using essentially the results of these experiments that we've worked on to do that. Now, once a hypothesis or a conjecture has been established, has been proven mathematically, then we're going to call that a theorem. In this class, our focus is on developing skills and developing a pattern recognition skill. So we're going to focus primarily on forming hypotheses and conjectures, or sort of playing around and experimenting. And we're not going to focus so much on the proofs in this class. So we're not going to be establishing theorems. But what you might see me do in this and future videos, and I've actually done in past videos as well, is we've experimented, we've done some stuff to observe a pattern, and then I'm going to state the theorem, or I'm going to state a fact. So we're going to make use of a fact, but we're not going to prove it or really establish it. We're just going to try and justify it a little bit based off of patterns. If you go and explore additional math classes after this one, then you might start looking into more theorems or deriving things, as opposed to the sort of like freeform playing around that we're going for. So let's look at those two theorems about what I was just kind of mentioning with our experiment. I feel like an old-timey teacher with overhead slides here moving things around. But our first theorem is that if you're multiplying a number by a tenth, a hundredth, a thousandth. Then you can find the result by moving the decimal point in the number to the left as the same number of places as there are zeros in the number you multiply by. This is one of those things that's like way more complicated actually to say formally than it is to do. So for example, here's what I'm going to do. I'm going to multiply 31 and 42 hundredths by 1/100th. What the theorem says is, hey, check it out. There are 2 zeros here. So I can move this decimal point 2 spots to the left, and I'm going to get 0.3142. That's what the theorem is saying. We'll do some more examples in a minute. But for instance, if we had 3 zeros there, if we multiplied by 1,000th instead of 1/100th, then we would have moved the decimal point over an additional spot. The same thing is true in theorem 2, but now if we're multiplying by a whole number as opposed to a decimal. So if we multiply by 10, 100, 1,000, or so on, now you move the decimal point to the right, however many zeros there are. So in 31 and 42 hundredths, if I multiply that by 100, I'm going to move the decimal point to the right 2 places because there are 2 zeros. And that's going to give me 3,142. If I bring back those experiments that we were playing with before, let me bring those back here, that's kind of what's going on. So if I look at 543.2, and when we multiplied it by 0.0001, let's see if that number of zeros matches what we should get. So here we have 1, 2, 3, 4 zeros. So if we move this 1, 2, 3, 4 places, we get 0.05432. Or if I have 6.789 times 1,000, there's 1, 2, 3 zeros. And if I move the decimal point to the right 1, 2, 3 places, I get 6,789. So these theorems that I'm stating follow what these patterns indicate that they would, lead us to conclude. So let's do a few examples. And notice that each of these examples, both numbers have a bunch of zeros. So we're going to be combining those two theorems together. Here's how I think of it. So I'm going to first do 4 times 3. That's what I'm going to do first, because that I know how to do. 4 times 3 is 12. Now, this 0 on the end of the 4 says that decimal, that's after the 12, needs to go to the right 1 spot. Then in 0.003, there are 1, 2, 3 zeros. So now this decimal point has to go to the left 3 places. 1, 2, 3. So in the end, we're going to get 0.120 or simply 0.12 because this extra 0 is unnecessary. Let's try another one. So here I'm going to ignore the zeros to start, and I'm going to do 5 times 3. So 5 times 3 is 15. And remember, with a whole number, the decimal point's off to the right, right? Like if you had $15, you would have 15.00. Now, in this 500ths, there are 1, 2 zeros. So I have to move that decimal point to the left 1, 2 places. Then in 3/10, there's 1 0. So I have to move it over 1 more spot. So 0.05 times 0.3 is going to be 0.015. Let's try one more. So on this last one, we have a 9 and a 3. And that's going to give me 27. Remember, with a whole number, the decimal point is just to the right, just like if you had $27, right? Now the 0.9 has 1 0, so that means we're going to have to move that decimal point to the left 1 spot. However, 3,000 has 1, 2, 3 zeros to the right. So now we have to move it 1, 2, 3 places to the right. And we end up getting 2,700. So I have a few more questions that you can work on to practice. In the next video, we're going to see what happens if we're going to multiply numbers that aren't just a bunch of zeros. What if there are different digits in each spot? So we'll do an example of generalizing the box method to multiplying with decimals, as well as the traditional method. So I look forward to seeing you then. In the meantime, I hope you have a wonderful day. Bye.